So there is first. Oh, thank you. First of all, we have something that we didn't end up last time in the last lecture with WKB. So I will start by. I will start with the WKB, just ending up our depth, and then I will move to the next topic, which is asymptotic estimations of integrals. Now we are on the edge with respect to ending up all the material. There are 3 lectures now, and I already did. There are 2 topics. One of them is the integration, asymptotic estimations of integrals, which is very important, though quite technical. And the other one is 2-time perturbation theory. So I will try to squeeze everything inside these 3 lectures as much as I can. But first of all, let's end up our discussion of the WKB approximation. So just to remind you, we have epsilon squared y double prime is q of x y. Last time I have tried to convince you that this is indeed the most general homogeneous second order equation, only that we have the epsilon squared in the coefficient of the y double prime, and we found that y is asymptotic to e to the plus minus 1 over epsilon square root of integral up to x of q of t dt divided by q to the power of 1/4, again up to a constant that we can deal with differently, separately. Okay? Are you with me? Good. Then we move to discuss the Schrödinger equation, where for us Schrödinger equation is epsilon squared y double prime equals q of x y, where q of now, okay, it's the same equation, where now if we want Schrödinger equation, then q of x is the square root of v of x minus the energy, okay, which is positive in the classically prohibited regime, negative in the classically allowed regime, and 0 at the turning points. Yes?
Why is square root?
Sorry.
Without.
Yeah, sure. This is. Okay? And then we, what our main project now is to see what's happened when we have a turning point that we conveniently put into 0, such that if I'm plotting q of x as a function of x, we have something like that. Right? This is our, we want to do WKB when we have a turning point. Now, we know that close to the turning point, the WKB breaks down because of this factor. We have 1 over q to the power of 1/4, and this, when this is 0, it explodes. So we cannot use WKB in this regime. Say that we call the region number 2, but we can use it in region number 1, and we also can use it in region number 3. And we did show, I'm not going to show it again, that there is an overlap between these regimes. So as epsilon goes to 0, there is some overlap between regime 1 and 2 and between 2 and 3. Of course, not between 1 and 3. But 1 and 2 and 2 and 3 have an overlap. Okay? Now, we wrote the solution. So the solution in region number 1 was simply y1 is a. Now I'm not sure that I'm taking the coefficient the same letters that I took last time, but forgive me for that. A e to the minus 1 over epsilon, yes, the integral from 0 to x, y0, it doesn't matter. It is independent. The choice of the lower boundary is just a rescaling of a, right? Of square root q of x, q of t, say, dt, over q to the 1/4. Okay? This is y1. Now, what is that's okay. So 1 is blue. 1 of the blue regime. Okay? What is y2? Y2 is b. Okay, why we didn't take here the plus thing? Because it explodes. Right? Y2 is b times area, and it was area of what? We had, okay, in the regime number 2, we approximated q of x. In regime number 2, we approximated q by ax. So the equation in regime 2 is epsilon squared y double prime is equals to ax y. That's it. And we know that the solution up to a scaling is A or Bailey. We are not taking Bailey. Why? Because Bailey again explodes and we have no chance to match it. But we take A, and we did find that the actual parameter here is A to the 1/3 times x divided by epsilon to the 2/3. We did this, I mean, we have a rescaling here, so you see it's ax divided by epsilon squared, and everything is to the power of 1/3. Okay? I mean, okay, we did that.
Yes.
Fine. So our first question was, what are the okay, and let's already write what's happened in region number 3. So in region number 3, we have C, just A, B, C, right? Times. Okay, now we have again this, we can again use the WKB, but now we have, okay, now the Q is negative. Right? Mm-hmm. So if we wanted to write it in terms of minus Q, we can write it as C times the, times this Q to the 1/4. We can write, okay, we can write it as sine of 1 over epsilon integral from x to 0 square root of minus Q of t dt plus divided by q to the 1 minus q to the 1/4. Okay? These are the solutions in the 3 regimes. Fine? Mm-hmm. Okay. Now, the question is now how to match them. And in order to match them, first of all, we want this solution in the regime of x much smaller than 1. Actually, we did find that it's x much smaller than epsilon to the power of 2/5 or something, if you remember. Right? We showed that last time, but x very small. Right? If x is very small, I can expand, I can take q of x to be ax. Simply ax, or at here, ax here. So what I will get is a here down here we have a to the 1/4 x to the 1/4, because this is ax. And now I have e to the minus 1 over epsilon, and I have to integrate over ax. So I approximate q by ax, right? And here I will have square root of a times 2/3 times x to the 3/2, right? That's the approximation of this expression, right, as x small. And note we did two asymptotics here. First we assume epsilon to be small to get the asymptotic, and then we take x to be small.
First asymptotic was global, and the second is local.
Yes. Now we have to match it with this expression in the limit of x large. X much larger than epsilon to the 3/4, to the 2/3, right? So this is x much smaller than epsilon to the 2/5. This is x much larger than epsilon to the 2/3. And in that case, this is the formula is b over 2 square root of pi. The 2 square root of pi is not something that we took from the local analysis that we did in the first lectures, because this is a number that has to do with the definition of the Airy function. You can define the Airy function differently. Then you have another factor here, right? Times e to this garbage to the 2/3 to the minus 2/3, and now we have this to the power of 3/2. So we have square root of a x to the 3/2 divided by epsilon to the power of 1. Which is good, right? We match exactly that. And now we have in the denominator, we have this to the power of 1/4. So this to the power of 1/4 is a to the 1 over 12 times x to the 1/4, and we have to multiply that by epsilon to the 2/2. 1/4 is 1/6. Okay? And by asking this and this expression to be the same, of course, what we have in the exponent is the same, otherwise what we did is garbage, right? And then we have the x to the 1/4 is again the same. So we found out that b must be equal to 2 square root of pi times epsilon a to the 1/6 times a to the minus 1/6. Right? Because a to the 1/12 and here a to the 1/4, then it's a to the minus 1/6. If we move it to that. Okay? This is the matching here. Right? Here. When x is way larger than epsilon to the 2/3, but way smaller than epsilon to the 2/5. Okay?
Yeah.
Good. Now we are going to match them here. Again, the x's, everything is the same except that you have to write minus x's instead of x. So first of all, what is the asymptotic of this expression? I think that I will have to go left a little bit, right? This expression, the asymptotic now, we assume again that this is minus a times minus 6, so this is ax, right? So what we are going to get is c divided by a to the 1/4 times minus x to the 1/4, minus x is positive, right? And here we have sine of 1 over epsilon times 2/3 times a to the 1/2 times minus x to the 3/2 plus v. Right? That's the asymptotic of the WKB expression as x goes to 0 from there. Now, this should be compared with the asymptotics of the area when the argument of the function is large and negative. We know that area changes its behavior, right? It is doing like that, right? If this is area as a function of x, then it is doing, here it goes down, like e to the minus 2x squared, and here it's, start doing something like that. Right? It's oscillating. And the asymptotics is b over square root of pi. Why there is 2 square root of pi here and square root of pi here? That has to do with the, again, with the definition. Times sine of, and we have b over square root of pi, and we have this, in the denominator we have this to the power of 1/4. So it's a to the 1/12 times x to the 1/4 times epsilon to the 1/6, and then we have sine of, because it has oscillatory behavior, sine of what? Of 2/3 now it's the argument to the power of 3/2. So square root of a divided by epsilon x minus x to the 3/2 plus pi over 4. Why pi over 4? Again, that's a way, that's a constant. There are 2 constants here. One of them is a coefficient, and one of them is this pi over 4. You can define it in a different manner, but it will not change the results. Okay? So we have to match this to that. How we are doing that? So first of all, clearly phi is pi over 4. That's the first, right? First, we see that phi must be pi over 4. This and that are the same expression. So we are happy. Okay? And then we want to this to be equal to that. So we see that that C is what? C is B over square root of pi times epsilon A to the power of 1/6. Good. And now by combining times B. B, yes, I wrote. So combining these expressions, what is the relationship between C and A? C equals to 2A. Good. So end of the end is that C equals to 2A. This was the goal of all this maneuver, right? To make a connection between C and A. Are you with me? Mm-hmm. Good. Now, so this is, I guess, the most glorious achievement of the WKB. Now you can ask what it is good for. Okay? So with WKB you can do many things, and the simplest of them is to get an estimation for the energies of particle in some potential, right? The quantum energies of a particle in a potential. So let's explain now how to do that. Suppose we have V equals to x squared over 4. What's the name of such a problem in quantum mechanics? Harmonic oscillator. That's an harmonic oscillator. Again, up to rescaling of h bar, m, all the other parameters, blah, 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 blah. We have that. Right? So how the potential looks like? You know that the potential looks like that. Right? It's a parabola. And if we define some energy, right, an energy, yes, how many turning points we have in such a problem? 2, right? So this is a tricky point. All this gymnastics was done in order to find what's happened in one turning point problem. Now we have 2 turning points. Let's call this turning point A. So this is at x equals A, and this turning point is B. B, small b. Right? Now, so what we actually have to do is to do the analysis here around A and to get this. To do the analysis here around B and to get, instead of A, B, and C, we have E, F, and G or something, but it will have the same form because we did nothing and this is just a reflection of this point. Yes, you see what I'm saying? And but what will determine the allowed energies? That's the question. So you see, I know how to analyze things here. What is missing, and this analysis and this analysis by itself is valid for any energy. I can define E. I mean, E is here into Q. I can define E whatever I like. What will make what is the requirement that will allow me only several values of E? Any idea? So again, suppose I have the solution here and suppose I have the solution here. What is the extra condition that I should satisfy? Matching both of them here. Yes. Matching both of them in this region. Right? So for the moment, let's think about the solution here. What's the difference between this? So the solution here. What region is in this? Region 3, right? So the only difference between the problem solved here and the problem solved here is the location of the turning point. Here we put the turning point to be at 0. Here the turning point is at A. But otherwise it's the same thing. So I can say that here the solution is what we call it C divided by Q to the power of 1/4 Q of x to the 1/4 times sine of 1 over epsilon integral from minus x, so this was minus x, from x to a, of square root of minus q of x, that will be q of c dt, plus pi over 4. Right? Again, the only difference is I'm taking from, if x is here, from x to a instead of from x to 0. It was minus x here because, but I'm taking from here to here. Doesn't matter. Same thing.
Yeah, but Israel is only in the region x from b to a, right?
X is smaller than a.
Yes, and greater than b.
What? And greater than b. Yes. Now, just for the sake of convenience, let's call it now C1. Now, how the solution here will look like? It's the same garbage, but we have to replace A by B, and now X is larger than B. So the solution in this region will be C2 times sine of 1 over epsilon integral from B to X square root of Q of X of T, sorry, of minus Q of T again, because Q is still negative, dt plus pi over 4, and here I have, down here I have Q of X to the power of 1/4.
Why it's a sinus and not like just in area 1?
What?
Shouldn't it be like in area 1?
No, because Q here is still negative,
Ah,
like here,
okay.
right? It's not. I didn't only shifted the location of the turning point, but also inverted everything with respect to X. Good.
But why we don't have the same solution?
What?
Why we don't have the same solution as near to the X equals A? Why is different solution? So,
I do not really understand.
we have a region from X from B to A, right? In this region, Q of T is less than 0. Right?
Both here and here, Q of T less than 0.
Yes. So why we just use only the first equation?
Of course, there is another solution here, which will be the mirror image of A, and so on.
Yeah, but second solution, you write it's near to the X.
The first solution is coming from here, the second solution is coming from here.
But it's the same region.
Yes, so
But
we want them to be the same. Okay, here we are. Here we are. That's the goal of this, of all this maneuver, is to say that now that we want these two solutions to be the same thing.
Shouldn't be minus Q?
yeah, mine
Should be minus.
Side.
On the second integral.
Yes.
The minus.
Q is
No, there
negative.
is a
minus
minus
here.
No, in the Mechane.
Ah, okay. But on both of them,
Yes.
I can absorb it into the.
Yes, yes.
Sorry, it's minus Q
Outside the...
to the 1/4.
Okay.
Yeah. Okay. So the question is, what are the conditions under which these two solutions are the same thing? They should be identical, right? Here, they should be identical. It's a wave function. It's the same wave function. Okay? So these two solutions must be identical through this region. Okay? Here is the trick. Let's write this one in the following way. I will write it as C2 over minus Q to the power of 1/4. Of course, I don't care about this. This is just the same as here, but times the sine of, and now I'm doing the following: 1 over epsilon times the integral from B to A of minus Q dt. Is that good?
You need to
No.
add from
Not
each
enough.
from A to
Okay,
X.
let's fine. I'm writing it minus 1 over epsilon integral from X to A of minus Q dt. You see? Do you agree with me that this is exactly that?
Yes, but you need plus pi over 4.
Okay? Now, instead of writing plus pi over 4, I will write it as minus pi over 4 plus pi over 2. So you are happy with this manipulation. It's garbage, right? I simply write. I wrote the integral in two different manners, and okay, good. And instead of writing pi over plus pi over 4, I wrote minus pi over 4 plus pi over 2. Okay? Now, what is important is that this is just minus the argument of this integral. Right?
Yes.
And so if I will call this sine of k1, let's call this the argument of this integral k1, right? Then this is, what is that? This is sine of k2 minus k1, where k2 is 1 over epsilon integral from a to b of square root of minus q dt plus pi over 2. Okay?
Sure.
Now, what are the conditions for this equality? Okay, first of all, I'm not exactly require them to be equal. I require them to be equal up to plus minus 1, because I can always choose C2 to be minus C1. I mean, right? So it should be plus minus there. So what are the conditions?
K2 is
Sine is equal to another sign if we add 2 pi, and is equal to the minus of the other sign if we add pi. So the conditions for that are K2 equals n pi, where n is 1, 2, 3, 4, and so on. Another way of expressing that is saying, we can say that 1 over epsilon integral from a to b of square root of minus q dt must be equal to, so we have n minus 1/2 pi, but I will write it as n plus 1/2 pi, where now n is from 0. Same thing. Good. So this is our glorious result.
but
This will determine the allowed energies of every quantum potential in the WKB approximation. As long as epsilon is small, it will give us, or h bar is small in the right scale coordinate, this will give us the energy.
איך אני אומר באמת?
מה? You can ask in Hebrew.
You express A and B in the form of E, and then you get an equation of E for E.
Yes. So let's start with the harmonic oscillator. Okay? We will start with the harmonic oscillator. So we started with this.
Yes,
Yes.
it's more a general physical question, but the Schrödinger equation is initially an approximation for low energy, and the WKB is an approximation for high energies. So,
No, I mean the low and high here are completely different. Low in terms,
Yes. So
low
we
is relativistic,
okay.
right? And high is
Is
high with respect to what is high? High, you want the rescaled h bar to be small parameter
compared to what?
compared to the other parameter whose dimension is angular momentum, right? H bar has dimension of angular momentum,
Okay.
energy times time. So the other dimension of angular momentum in the problem should be h divided by z should be small. Okay. So now let's do that for harmonic oscillator. So for the harmonic oscillator, what we know that
A equals minus A.
but okay, so the A and the B, the location of the A and the B are simply plus minus. The turning points are at x equals plus minus. We want x squared over 4 to be E, right? So x is plus minus for the square root of 4e. So what we have here is 1 over epsilon integral from A to B, from minus square root of 4e to square root of 4e, or square root of e minus x squared over 4 dx. This is the integral.
This is need to be equal to.
This has to be equal to n plus 1/2 times pi. Now, what is that?
Isn't it just alpha circle?
Okay, we can write now y as we will define. Okay, first of all, let's take square root of e outside. So we have square root of e divided by epsilon, integral from minus square root of 4e to square root of 4e times square root of 1 minus x squared over 4e.
So it just
Yes.
a half of a ellipse.
So we want y, we want to define y to be x over square root of 4e. Okay? And now we will have as follows. We have square root of e divided by epsilon, integral, if x is, this is minus 1 and 1 now. You see? Minus 1 and 1. Now we have square root of 1 minus y squared. This is that. And we have dx. dx is square root of 4e times y. Okay? So we have here dy. And we should multiply here by 2 square root of e. Overall, we are going to have 2e. Okay? And now, what else we need? Now we have to solve this integral. From minus 1 to 1.
Just half a circle.
Clearly, we can define now y to be cosine theta. And dy is, y is sine theta. Dy is cosine theta d theta. Okay? And the integral, and we have 2e over epsilon, integral from minus pi over 2 to pi over 2. Okay? Of now 1 minus y squared is again cosine theta. It's cosine theta squared, so the square root of cosine theta, and we have cosine squared theta d theta, and this is pi over 2. Right? It's 1/2 of the integration. So all in all, what we get is e times pi divided by epsilon. And this must be n plus half times pi. So the pi cancels out. And what we will get is E, the En, the energies of the harmonic oscillator, are epsilon times n plus 1/2. And now if you take epsilon to be h bar over square root of m omega or something, I mean, you get the correct result.
H bar.
Okay? H bar over square root of mk or something. You got the same result. So these are, in this case, we had a miracle that not only we get an approximation for large energies, we got the exact energies. Right? But this is not this is not guaranteed by the manufacturer. It's a local little miracle. Okay? Now, but yes, but you already know. You already knew what are the energies of the harmonic oscillator. The point is that now we can estimate every. I mean, we have an estimation. To what extent it is correct that, I mean, we have a large energy estimation for any potential. What happens, for example, if we are taking x to the 4 over 4? What is that? It's a quartic potential. So it's a little bit more flat here. Something like that. And the xc now will be plus minus of 4e to the power of 1/4. So if we go to here, we have minus 4e to the 1/4, and here we have 4e to the 1/4, and here we have x to the 4. So we can now, again, we have here minus 4e to the 1/4, and here we have 4e to the 1/4. Now, we have square root of e here, okay? And we have here x to the 4 divided by 4. So we will define y as x to the 4e to the 1/4. And this will allow us, okay, so now we have, now dx, okay, so this will be square root of 1 minus y squared, fine.
No,
Y to the 4th, sorry, y to the 4th, right? This will be minus 1 and 1, but the dx is now this times dy. So instead of having, here we have the square root of e, right, that we had here, and now I have to multiply it by 4e to the 1/4. And that's it. I think, yeah. Am I right? Is that it?
Yes.
Yes. Okay? You see? Now, this integral is some beta function. I'm not going to elaborate on this integral because we have no time, right? But still, you can see that what you get from this integral up to numbers, right? So the result will be C1, some number, right? Times, what is important, e to the power of 3/4. Because we have square root of e and e to the 1/4, and all the rest is e independent.
Just a number.
What?
Just a number.
All the rest is a number. And this should be equal to, again, over epsilon. This should be equal to n plus 1/2 pi. So again, you see that the energies, the eigenenergies, are proportional to n plus 1/2 to the power of 4/3. That's, I mean, up to factors, blah, 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 factors. This will be the result.
If we compute the factors, do we get again exactly the?
No.
Is there
Now
a
it
way-
will be exact only in high energy.
No,
Is
what
there a
do
way
you
to
mean by
find the
exactly? It's
error?
not solvable.
What?
It's not. What do you mean by exactly?
Now you will approximate.
No, yeah. It's
The higher is the energy, you will approximate it better and better and better.
Yeah,
I
the
meant,
problem
is there a way to
There's no
to
exact
find the
solution.
error?
Can, yes, calculate the 1 over epsilon squared. I mean, the next order in the WKB, calculate S2, and then you will find something about there. Okay? And of course, what will happen if I will write here in 4m, say, where m is a number, 2m, right? When m is a number, m is 1 is harmonic oscillator, m2 is quartic oscillator, and so on and so forth. then this x will be plus minus 4e to the power of 1 over 2m. Right? So I will have here 1 over 2m, 1 over 2m, and x to the 2m. So again I have a square root here, but here I have x to the 2m, and this will be 1 over 2m and 1 over 2m. Right? So when y will be x over 1 over 2m, okay? So I will get here the square root of e times e to the power of 1 over 2m. You see? So in general, I'm finding that I will get here a 1 plus 1 over 2m.
Half.
Uh,
The first term is half.
It's the square root.
The square root. 1 half
Sure.
plus 1 over 2m, so it's 1 half of what?
M plus 1 plus 1.
It's 1 half times 1 plus 1 over n. Right? So e will be n plus 1 half to the power of 1 over z, which is 2 over 1 plus 1 over n. Right? So m equals 2 is harmonic oscillator. We have 2 over 2, 1. M equals 2 is a quartic oscillator. We have 2 over 3 halves. It's 2 over 3 halves is 2 times 2 thirds is 4 thirds. Now, as m goes to infinity, what are you going to get? 2. Right? Now, what is m goes to infinity? If m is going to infinity, it will be 0 everywhere when x is smaller than 1, and 1 everywhere when x, infinite when x is larger than 1. So it's what?
Yeah.
It's a box. And this is a right, for particle in a box, the energies are going like and the En is going like n squared. Good. So, all this is actually known, this is known as Bohr-Sommerfeld approximation. So as you know, when people have realized that classical physics is broken because of the experiments on the black body radiation and other things, then first Planck invented the quantum physics by putting restrictions that the energies of the harmonic oscillator, say, are n plus n to the is equally spaced, right? And then there is some unknown constant h that controls the damn thing. And then people start thinking about what happened in the generic case. Okay? So the idea of Bohr and Sommerfeld was to stay with the classical physics, but to add a global constraint. Right? It's like a big patch putting on classical physics in an attempt to. And what is this constraint? This constraint is that. That's the Bohr-Sommerfeld approximation, right? So they say take only trajectories. Now, what is square root of minus q? Remember that this is E minus V. Now, what is E minus V? This is the kinetic energy. And the square root of that is the momentum. Again, up m equals 1, everything, right? So the idea of Bohr and Sommerfeld was that 1 over epsilon, which is h bar blah blah blah, integral over the momentum times dx in a back and forth should be equal to n plus 1/2 pi, maybe they have a 2 because they took the integral back and forth or something. But this was their idea, that you can get all the quantum physics by taking just classical physics, but imposing a constraint that for each particle which is trapped in a potential, you accept only those trajectories that satisfy their condition. This was the idea of Bohr and Sommerfeld. Now, people have tried that and it fails. Well, it was fine for the hydrogen atom, but it fails for the helium, right? And that was a reason why Schrödinger and Heisenberg understood that they have to invent something from the scratch. But now, if you want to see why the idea of Mr. Bohr and Sommerfeld is working, it is the basis is WKB. So it should be a good approximation when we are close to the classical limit. Okay? Good. So, so this is, wow. I spent way too much time on that. So this was our story about WKB. Okay? Now we are moving to another topic, which is estimation of integrals. Okay. So I will start, the question is, you have an integral, you put it on in Mathematica, you hit the button, you write integrate blah 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 from x equal to x equal right? You hit the button and it starts thinking, and after 1 minute, say, it is writing the same integral again as an answer, meaning that I don't know how to solve it. Or you put the integral and it says, yes, this is hypergeometric function f 1, 2, 3, 4, 5, 6 with 85 arguments, which is garbage as well, because you don't know what to do with it. It's not like a sign. You don't know what, you have no idea how to deal with it, and it gives you no information despite having a name. So maybe you can, in some cases you can publish a paper with such a result, but as a matter of fact, it's not better than, integrating numerically the thing. It will give you the same insight but with the same effort, right? So the question is what to do. So what a physicist should do, in any case, is to look at the problem and try to identify small parameter or big parameter and solve it there, and then try to expand around it and blah 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 blah. Okay, so now this is what we are going to do now. Until now, our small parameter or big parameter was the distance from a point or epsilon in differential equations. Now we have to think similarly about integration. Okay, and I will give a few examples. First of all, let's look at the integral. This one. Let's look at the integral of from 0 to 1 of sine xt over t dt at x going to 0. Okay? You want to know how this garbage behaves when x is small. What you can do? What? Taylor expand, exactly. So this is first method we are, the first method, expand the argument, the integral. Right? Just expand it. So I'm going to write this as the integral from 0 to 1, or sum from n equals 0 to infinity of minus 1 to the power of n divided by 2n plus 1 factorial x to the 2n plus 1, and now I have the integral from 0 to 1 of t to the 2n plus 1 divided by t. See? And so this is the integral over t to the 2n, and the answer is x to the 1. Okay, so what I have is sum from n equals 0 to infinity of minus 1 to the power of n divided by 2n plus 1 factorial times x to the power of 2n plus 1, and now we have from 0 to 1 of 2 to the 2n plus 1 divided by 2n plus 1, which gives us sum from n equals 0 to infinity of minus 1 to the power of n x to the 2n plus 1 divided by 2n plus 1 times 2n plus 1 factorial. Okay? And so if we want to write it term by term, then for n equals 0, we have x divided by 1 times 1 factorial. So the first term is x. The next term will be minus, and here we have x to the third. And here we have 3 factorial, which is 6 times 3, so we have 18. And the second term will be x to the fifth divided by 5 by 5 factorial, which is 600. Okay? We have a full power series by expanding the okay?
Yeah.
Now, okay, so I will give more examples in the I will give much more examples in the Targil, and let's move. Okay, I don't want to elaborate on that because this is quite trivial, right? Next, I will give more examples in the Targil. So, next method of finding right. Next method is integration by parts. To remind you, if we have an if we have an integral of u dv, this is from A to B. This is the endpoints of u v minus the integral from A to B of v du. Okay? You have taught, they taught it when you were 8th grade or something, right?
8 years old.
Somewhere during your high school studies. You should have good. So now let's ask, how do I estimate the integral e to the minus t to the 4 dt from x to infinity when x now is large? What?
It's e to the minus t to the 4th.
It depends on x.
Yes, it's fine.
Yes.
T is not in the right. I want to know what is the expansion of this when x is large. Okay? what should I do? The trick is to write I as the integral from x to infinity of d dt of e to the minus t to the 4. And now, this will give me, if I will have only that, it will give me minus
40 cubes.
minus 40 cubed. So I should write it as minus 1 over 4t cubed dt. This is absolutely kosher, right? And now I will define this to be my dv, and this to be the u, right? So this will give me from x to infinity of e to the minus t to the 4 divided by 4t cubed minus the integral. I have a minus sign here? Yes. Yes, because I will put it's a lower bound that will dominate. Minus integral over what? Over, so it's plus, right? E to the minus t to the 4 dt. And I have to take the derivative of this. Right? So the derivative of this is, we have 3/4 times t to the 4, and I think I have an extra minus. Okay? You see it? Now, fine. So what we got? From here, we get e to the minus x to the 4 divided by 4x cubed. And I will claim that this is the first approximation in a series of 1 over x when x is large. Right? Why? Because now this is the correction. How do I show that the correction is much smaller than this? Is indeed much smaller.
Just take a limit. Go divide 1 to the second one. Limit.
But how do I calculate that? That's a question. I don't know how to
do
calculate.
the same trick, and you have an
Wait. It's from x to infinity, of course.
Okay.
So how do I show that this is much smaller? The answer is that the integral from x to infinity of e to the minus t cubed over t cubed dt is much small, is negligible with respect to 1 over x to the 4, sorry, is much larger than 1 over x to the 4 e to the minus t to the 4 dt from x to infinity. Or maybe I will write it
Shouldn't it be much smaller because 1 over x goes to infinity?
no, for every finite x.
Ah.
Here you integrate and the denominator is getting smaller and smaller as you increase the denominator is getting larger and larger as you increase t, right? And this is the smallest value it takes.
Okay.
This is the smallest value it takes. So this must be much larger than that, right? Because that's yes. And because of that, the correction is negligible with respect to this term. Okay? And now you can continue, if you want to continue what you do, yes, you write now this as ddt of something, and you see that the next term will be x to the 7, 1 over x to the 7th or something like that. Right?
Still not convinced why does it prove that the second term is negligible in the system?
What?
Why the condition you wrote down claims that the first term is
t to the fourth is always larger than
No,
x
yeah.
to the fourth.
I agree with this, with that condition, but how it convinces that the first term in the first line, which we calculated, is much larger than the second, which is the correction.
Because
You calculated the correction and you claim that it's much larger than something else, but didn't put an upper bound off on the correction. You just gave a lower bound of it. Can't prove that this term is smaller than something else, just that it's bigger than something else.
wait. Again, what you are saying? No. You are saying that yeah, because this is, by definition, I, the original integral,
Sure.
over x to the 4.
Yes. Okay.
Sorry. This is smaller than.
Now
This is smaller than. Yes. Because, again,
Otherwise, it's just a
yes,
lower
this
bound.
is smaller than because this is growing,
Yes.
right? And this is not growing here. Okay.
Now that's fine.
And so now you see that it is negligible, as x goes to infinity, it is negligible with respect to the original integral.
Negligible with something that's not smaller than the action.
The correction is negligible with respect to the integral over x is smaller than the integral divided by x to the 4. So of course it is much smaller than the integral itself as x goes to infinity. Okay. Again, I will do more examples in the exercise. Right. Now, so this is the second. So the second method is integration by parts. Okay, and now let's move to the third method, which is the most interesting one, and we are not going to exhaust it today, but I want at least to explain what's the essence of it. And these are Laplace integrals. Okay. What are Laplace integrals? Okay. Laplace integrals refer in general to integral. How fast they get? It's unbelievable.
Really fast.
Really? I mean,
Maybe you need to close it.
Yes, if you close it, it's better, but not really much better.
unbelievable. Okay. So, an integral is the Laplace integral if it has a form integral from a to b of f of t times e to the x times phi of t dt, and we want to evaluate it as x goes to infinity. So we want to approximate this integral as x goes to infinity. Now, try to concentrate because we are going to show a fantastic trick. Well, let's, this is A and this is B. We would like to integrate from A to B. And let's assume that that phi. I don't have any other working. What is that? No, this is red also. Let's assume that phi is looking like that. Where the main contribution to the integral is coming from?
That's maximum of the phi.
Clearly, as x goes to infinity, the main contribution will come from here.
אז become a delta.
Okay? So what I'm saying, I will claim that if this is, say, C is the point of the maximum, okay? Then this integral is asymptotic to the integral of f of t e to the x times phi of t dt from c minus epsilon to c plus epsilon. So instead of having all this integral, I'm actually integrating only from here to here. Because x goes to infinity.
So just FC.
What?
So you're saying just FC?
Oh. Now we are allowed to do an approximation because we have limited the range of integration to such a small region, right? We have a license to say that in this very small region, f of t will be f of c, and I can get it out of the integral. You see? Now, what about, and now I have to integrate from, what about phi?
Phi of c, so you can take it also out of the integral. E to the x phi of c.
Okay, but let's be a little bit more careful. I will say that phi of c, phi of t is phi of c plus phi prime of c times t minus c plus phi double prime of c times t minus c squared over 2. Okay, I expand. Okay, now, what can you say about this expansion?
Second term.
The second term must vanish. Why? Because this is a maximum. So by definition, the second term must vanish. If the second term vanishes, then I can write it as f of c times e to the x phi of c, that again gets out of the integral, times the integral from c minus epsilon to c plus epsilon, right, on e to the x over 2 times the second derivative of phi at c times t minus c squared dt. Which is, okay, now I can change the coordinates to, I can measure distances, I can write tau as t minus c, right? And this will be f of c e to the x phi of c, an integral from minus epsilon to epsilon e to the x over 2 times phi double prime of 0, because c now is 0, right, times tau squared d tau. Okay? Now, here comes the horrible thing.
Shouldn't the phi still be c because you don't have any t there? It's just phi of c.
Inside the
Yes, it's a constant.
inside the second derivative you plug should be
Okay, whatever. Don't matter. You can change the name or not change it. it's enough. Now I can say, now we are doing something that looks horrible. And we are saying, okay, this is the Gaussian integral. Okay? But we have to integrate only from minus epsilon to epsilon. Right? However, x is going to infinity. If x is going to infinity, it implies that the Gaussian integral is very sharp. So we can do the next approximation and do it from minus infinity to infinity.
Yeah, but
But epsilon goes to 0.
It works. It works. Okay? That's a horrible trick here.
yes,
Right? We evaluate everything here, and now we know that everything that is going, every correction, so every correction which is, you know, what are the corrections? We have a Gaussian, right? And the corrections are these. The contribution of this correction is subdominant as x goes to infinity. So we are allowed to do that.
Also epsilon goes to 0, so
No, it should be.
Okay? That's a trick. And what is this? Okay, I forgot it. There is a final result here. Right? This is the Gaussian integral e to the alpha x squared. It's square root of pi over alpha.
It's a maximum for the
There is a
for the second
minus.
derivative. Yes, should have a
There is a
minus
minus.
everywhere.
Oh, okay. So if you want me to do that, I have to write this.
Yeah.
Because phi double prime is negative. So if you want me to have the minus, I should take the absolute value of pi double prime. So the final result is f of c
Yes.
times e to the x phi of c square root of pi 2 pi divided by x phi double prime of c. Absolute value. Right? This is Laplace estimate for such an integral. Okay? So this is Laplace method. Right? You look at the integral and you find that and you are happy. Okay? When this method, however, may fail. When? Even if x is going to infinity,
there is no
it
maximum.
will fail when there is no maximum in the range of integration. So suppose phi of x is something like that, right? Then we have no maximum in the range of integration. What should we do?
Shift.
Take the first one.
No, we have to take, but there is still a maximum.
Yes.
There will be a local maximum here or local maximum here. So either I have,
Global, not local.
what? Global maximum. So
Yeah.
we have global maximum either here or here. If there is a maximum on both sides, what we should do? We should take both,
Yes.
right? But as long as we have, right, one maximum here, however, now the derivative shouldn't be 0, right? It may be something like that.
Yeah.
There is no guarantee that the derivative is 0 at the point of the maximum because it's a maximum only because we have a wall there. So in that case, we will have, so suppose the maximum is at A.
So we take
Okay.
the first,
So we have now phi of t is phi of A minus phi prime of A. Again, absolute value times t minus c. And we don't need the next step, right? Because this term now do not vanish.
Y minus?
Because I took the absolute value, because it must go down. Just to...
Yeah, but it depends on the side where the maximum.
I assume that t minus b. This was a. T minus a. Okay?
It's plus if you have the maximum on the other
Yeah.
side.
Yes. So now I'm starting from here, and this is now from a to a plus epsilon of that, and now I can write the f of a and phi of a, and here I have x from a plus epsilon to a minus epsilon, x times what? Minus x times the absolute value of phi prime of at a
Wait, the integration starts from a, not from a minus.
times t minus a.
The integration is
From
from
a. So, yes. And again, so we have this outside. And now I can replace it by an integral from 0 to infinity, right? On e to the minus x phi prime of a times tau, no squared, d tau. Right? Now it's not a Gaussian integral, it's just an integral over, where again I expand the range of integration to infinity, and what I will get is f of a times e to the x phi of a divided by x times phi prime of a. Right? And what will happen if the maximum will be on the other side?
They will get the same.
Same thing, just replace a by b, right? So this is the asymptotic of integrals by using Laplace method. Okay, so I will postpone the examples to the Targil, and I have one sophisticated example with tricks. And I mean, for all these things, I will give many examples in the Targil. Now, what about homeworks? I didn't plan my time appropriately, so I don't have still homework for you for this week. But just to make sure, you already get one Targil on WKB, right?
No.
No?
No.
Nothing WKB?
No.
Boundary
So what you did last week?
We didn't get any homework.
No, not homework. I mean, what about the Targil itself? He did WKB.
Yes.
Okay, so you didn't get homework on WKB
Yes.
at all?
At
At all?
And also
about
boundary
boundary.
Also about boundary layer?
Yes.
Yes.
Wow. He was smart not updating me and escaping to the army. Okay, now I have to accommodate with all the garbage. Okay, fine. So I will prepare something. Again, I didn't plan my time appropriately. Today was a crazy day, so we will have a exercise in half an hour from now, and I will update you by email when the exercises will be on, when the homeworks will be on the Lambda or whatever they call it. Okay? Right. So in the lecture we have presented 3 methods of evaluating the asymptotic expansion of integrals. Now let us take a few examples from each of them. Good. So, first example, let's take the integral from x to infinity of e to the minus t to the fourth dt. This is I. Actually, this is an integral that we evaluated in the lecture in the limit where x goes to infinity. Now I want to evaluate the same integral at x goes to 0.
It's extension.
What?
Just this extension.
Okay. So the way to do that, what you suggest?
Extend the integral.
Yeah. Yes. So okay. So but it requires a little trick. The little trick is to write it as an integral from 0 to infinity of e to the minus t cubed t to the fourth over dt minus the integral from 0 to x of e to the minus t to the fourth dt. And now this integral we have to solve, right? And this here we can expand it because now t is small because x is going to 0, right? So what is, first of all, what is this integral? This integral, the integral from 0 to infinity of e to the minus t to the fourth dt, we can define now q as t to the 4. So t is q to the 1/4. So dt is 1/4 q to the 1/4 minus 1. I'm writing it that way. So this is the integral from 0 to infinity of e to the minus q times 1/4 times q to the 1/4 minus 1 dq. Good. What is that? Remind you the definition of a gamma function. Gamma of a is the integral from 0 to infinity of t to the a minus 1 e to the minus t dt. So this is gamma of what? So this is 1/4 gamma of 1/4. And what is that? Again, I will remind you that gamma of z plus 1 is z gamma of z.
So
this is gamma of. So we have gamma of 5 quarters. Some number.
This is like writing the hypergeometric function.
Why? It's a number.
Also the.
No, hypergeometric. Now
no.
we want to change the
I mean,
argument.
how you calculate this? By numeric?
What?
How you calculate the value of that number? By numeric?
Yes. Some of them are evaluated analytically, but in general, yes, this is
You don't have 3 parameters, just 5
Yes.
or 3.
just a number. Minus, and now we can write the sum from n equals 0 to infinity of the integral from 0 to x of t to the power of 4n, t to the 4n divided by n factorial dt. Minus 1 to the power of n. Actually, the n factorial is here. Okay? So what we have is gamma of 5 quarters minus sum from n equals 0 to infinity of minus 1 to the power of n divided by n factorial t x to the 4n plus 1 divided by 4n plus 1. So this is gamma of 5 quarters minus what will be the first term? N equals 0. We have x, right? And the next term will be plus n equals 1. So we have x to the 5 over over 5. Yes? For some reason I don't like the answer, so let me try to check if this is... Yes? Okay. And the next term will be, again, minus, now n equals 2.
X to the 9.
So we have x to the 9 divided by 2 times 9. So times 18, blah, blah, blah. Okay? Expansion in x. Good. Any questions about that? This brings us to a discussion of the incomplete gamma function. Which is something that is worth being familiar with. So the incomplete gamma function, gamma of a and x, is by definition the integral from x to infinity of t to the a minus 1 e to the minus t dt. Right? And one may be interested in the expansion of this at x goes to 0.
It was in the homework.
What?
It was in the homework.
It was in the homework. All the cases?
No, it just was. It was e times x times the incomplete gamma function to pad 8.
Ah, okay. But now we want analytic expressions. Okay? So, what can we do? We can write it as, okay, there are 3 cases that are in fact 2. It's important to know that. I'm not, the expansion by itself is quite tedious, but you know that how the gamma function looks like. So if this is x, and, a, and this is gamma of a, you know that it is doing something like that, right? And it diverges for 0 and negative integers. Okay? So here, I mean, when as x goes to 0, if a is positive or non-integer negative, then the limit as x goes to 0 is finite. Right? Whereas if x is going to, if a is 0, minus 1, minus 2, then we have something that diverges as x goes to 0. You see my point? Okay. Now, so let's assume for the moment that a is larger than 0. And if a is larger than 0, then the integral, you see, when you integrate, when you are very close to 0, e to the minus t is more or less 1. And we have t to the minus 0.9, say. Minus 1 minus a, and this is a converging integral. Okay? So if a is larger than 0, what we can do, we can write it as the integral from 0 to infinity of t to the a minus 1 e to the minus t dt minus the integral from 0 to x of t to the a minus 1 e to the minus t dt. Now, this is simply the gamma function of a. And this we can expand. So we can write it as gamma function of a minus, and now what we can expand? We can expand it to the minus t. Right? Because the region here is x is small, so e to the minus t can always be written as sum from n goes to 0 equals 0 to infinity of 1 minus 1 to the power of n divided by n factorial. And now we have an integral from 0 to x over t to the n minus a plus a minus 1. Yes. Yes? Yes. Yes. And this integral is simply x to the n plus a over n plus a. Therefore, the final answer in the case a larger than 0, in this case, is gamma of a minus sum from n equals 0 to infinity of minus 1 to the power of n divided by n factorial x to the n plus a divided by n plus a. Okay? Now, good. This is the simplest case. Now there is an ugly case where a is negative, right? When a is negative but is not an integer, right? How do I say that?
It's not integer.
Right? If a is negative but not an integer, it's hard work because you can't do that naively because this, okay. In any case, I don't want to elaborate on that. You get the same answer. Miraculously, you get the same answer.
Even with all of the divergence inside,
Despite the fact that this
you should stop the integral. And
series formally diverges, because if a is minus 5, say, right, and n is 1, then we have here, or a is not minus 5, minus 5.5, right? And n is 1, then we have here minus 5.5, right? And this diverges in the lower bound. Still, after maneuvering, you get the same answer. Weird, but wait, is that the same answer? Yes. Okay. Now, the most interesting case is a case where a is 0, minus 1, minus 2, and so on. Let's speak about the case a equals 0. If a equals 0, we have here the integral from x to infinity, gamma of 0 and x is the integral from x to infinity of t to the minus 1 e to the minus t dt. Okay? Here is a trick. We can take the derivative of this with respect to x. What is the derivative of d gamma of 0 of nx with respect to x?
or just the integral.
It's minus
Minus the integral.
the plugging x in the integrand instead of t. So it's minus 1 over x e to the minus t,
Minus x.
e to the minus x, sorry, which is minus 1 over x times 1 minus x plus x squared over 2 minus x cubed over 6 and so on and so forth,
So just integrate.
which is minus 1 over x plus 1 minus x over 2 plus x squared over 6 and so on. So this is their derivative. That's very easy. Now, how do I get the function itself?
Integrate.
I will integrate, right? So integrating that, I will get what? I will get minus ln x plus x minus x squared over 4 plus x cubed over 18 and so on and so forth. Okay? Did I do is that the answer? Of course not. Otherwise I wouldn't ask. But what is missing? Constant. So the question is, we have a constant here. And the question is, what is a constant? Okay? It turns out that in that case, the constant is, yes. So the constant is minus gamma Euler. What gamma Euler is? Gamma Euler is a number, like E and pi, right?
Yeah,
Gamma Euler is 0.5772 something, and is by definition the limit of sum from n equals 0, from n equals 1 to n of 1 over n, minus ln n as n goes to infinity. So the sum over the harmonic series minus ln as n goes to infinity is converging to gamma Euler.
How can you show that actually?
Good question. I checked once, but I don't remember. Okay?
In this integral, how can you find the constant? That's generally. What steps should you do for finding the constant? Given this integral.
You have, I think that there is a question in Bender that requires you to find the constant of integration, and they explain how it works. Good question for homework. It's let me see, chapter 6.
It looks like taking the limit at x goes to infinity.
Yeah. What about it?
Yeah. But I don't know how to do it. Just look.
Yes. This is why I asked.
Yeah, so it's question 6.5 in Bender's book, and it's classified as difficult. So, good luck. Okay? Okay? And so importantly, this diverges as it goes to zero, as required, right? The integral diverges as x goes to 0, and this should be the true for all the negative integers, right? Now, so people have already, of course, looked at this, and because it was explored, it had a specific name. So instead of calling it incomplete gamma function, there is another name for it, namely the exponential integral. And it appears so many times that it's better to be familiar with that. So the exponential integral e 1, say, I have to work with, okay? So E1 is gamma of 0 x, that's E1 of x, and its asymptotics is what is written here. So it's minus gamma Euler minus ln x plus x minus x squared over 2 over 4, blah, blah, blah. Right? In general, the exponential integral of k of x, right, is gamma of minus k minus 1 x, right? And it is given by the following expression.
K is integer or
Wait. So this is C. Gamma, this is E1, this is E n plus 1. So minus n and x, right? Just, and this is given by Cn plus minus 1 divided by n factorial to the power of n plus 1 times ln x minus from n equals 0 to infinity minus 1 to the power of n Yes. Let's see if this is if this works for the n equals 0, right? So for n equals 0, we have C0 that we know is minus gamma Euler.
How do you define the C of M?
What?
How do you
The
define
constant.
C of M?
Okay, I told you only what C0 is
Yes.
for the moment. Yes, just to make sure. C0 plus, we have minus 1 to the power of 1, so we have minus ln x minus, and now we have n from n equals 0, but n is not equal to n, so we don't have 0, we have 1, so we have minus 1 to the power of 1, so it becomes plus x to the x divided by 1 times 0 minus 1, yes? Yeah, I have x, small n is 1, large n is 0. So I have here minus 1 to the power of 1. So I have plus here x to the n minus 1. Why don't I have a minus from here? That's my question.
Maybe it's the opposite.
Yes. Small n minus large n. So now it's fine. Plus x, and the next term will be small n is 2, so we have minus, and we have x squared over, now we have 2 times 2 minus 0 over 4, and so on and so forth. Right? Well, C naught is gamma minus gamma. Good? Now you may ask, what is Cn? Okay, so the formula for Cn is the formula for Cn is minus 1 to the power of n plus 1 divided by n factorial times gamma Euler minus sum from n equals 1 to capital N over 1 over. Okay? So again, C0 will be what? Will be just gamma Euler. And what will be C1 say? C1 will be minus 1 to the power of 2. So it will be 1/2. No. C1.
Gamma Euler.
Right? So we have gamma Euler plus minus. Yes, minus 1. And so on and so forth. Good. So this is, okay, maybe it's better to write what is E2. Okay, let's write it. I want to have, so C1 is gamma Euler minus 1. So what will be, this was E1, gamma of 0, and now let's write gamma of 1 and x. It will be, as we said, gamma Euler minus 1, right? And what else we have? That's the C. Now we have a plus, right? A plus what? Plus ln x. And capital N is 1, okay? Plus ln x. Yes, okay, fine. Note that whereas this thing goes to infinity as x goes to 0,
Yes.
this is going to minus infinity because that's a gamma function. So I have plus ln x, and now I have minus, what's the next term? Now I have the zeros order here. So I have what I have 1 over x, right? If n is 0 and capital N is 1, then I have here minus 1 over x. The question is
With a
no,
plus.
with a plus.
Plus.
Yes, plus 1 over x. Okay, so the divergence of this one is stronger than the divergence of that one. Right? What will be? And now we have no 1, but we have 2. What is the answer? What we have for 2? Again, we have plus because of that. So small n is now 2. We have x to the 2 minus 1. So we have x divided by 2 times 2 minus 1, which is 1. Yes.
It should be minus.
Why minus?
Because small n is 2.
Must
And,
changing signs.
Yeah.
One of them
Small
must be
n is
minus.
2.
Yes.
So okay, so
No,
this
no.
is plus, this is minus. Yes.
No, it was right.
What?
Plus and
Minus here?
Yes.
Yes.
You actually
from n equals 0.
you actually draw it over there.
Okay.
You
Yes.
can
Start
see
with
that.
n equals 0.
Minus.
Yeah.
Then you get
Okay. So this is the story about the incomplete gamma functions. Good. Now, having said that, we can do a very interesting exercise. Which is not exactly one of the 3 methods of this, but it's asymptotic. It's asymptotic matching. So it's an exercise. You did have an exercise on asymptotic matching. It's just that you don't have homework about it.
Yes.
Okay, so maybe I should. No, I will do that. I can give a homework question in the same spirit. Okay, so let's try to calculate the integral from 0 to infinity of e to the minus t minus epsilon over t dt as epsilon goes to 0. You see that there is a boundary layer. How do you see that? You plot the integrand, right? Just plot the integrand. So if epsilon is 0, the integrand is going like that. It started at 1 and going down like e to the minus t. That's epsilon goes to 0. But for any finite epsilon, no matter what, when t is much smaller than epsilon, this term will blow up. So it will be something like that. And if I'm taking even smaller epsilon, it will be something like that, and so on and so forth. So the answer will approach the epsilon goes to 0. It's a regular perturbation theory. Yes, it's a regular perturbation theory because as epsilon goes to 0, okay. First of all, what's the answer when epsilon goes to 0? 1. You agree? Okay. So now we want to find the first correction in epsilon to that, right? Here is the trick. I will define a new parameter, which is not in the problem, but is small, and this is delta. Now, delta will be such that will be also small. What we can say about the smallness of delta, that's the relationship between delta and epsilon, this is a question, but we are going to assume that both delta and epsilon are much smaller than 1. Okay? And I will divide the integral into an integral from 0 to delta on e to the minus t minus epsilon over t dt plus an integral from delta to infinity of e to the minus t minus epsilon over t dt. By the way, okay, it is also an exercise on just using the first method, so expanding the. Okay. So what we are going to say? So in this regime, when delta is large enough, right, this term is negligible. That's the idea. You see? In this regime, where delta is very small, this term, this t is negligible. You see? So I can now write these two integrals as an integral from 0 to delta on e to the minus epsilon over t. Sorry, I wrote the t times 1 minus t plus t squared over 2, say. Okay? Plus an integral from delta to infinity on e to the minus t times 1 minus epsilon over t plus epsilon squared over 2t squared, and so on. So I'm expanding the two terms. Now, I will calculate this and calculate that and add them together. However, I must make sure that delta do not appear in the answer. Because delta is an artificial parameter that I introduced here just to separate two types of behaviors. And clearly, actually, why it is matching? Because I can choose delta such that there is a region where both epsilon over t is, here we assume that epsilon over t, that t is small, right? And here we assume that epsilon over t is small. So we can choose a case where both of them are right. For example, if delta is square root of epsilon, say, then t is small, right? If I'm choosing delta to go like square root of epsilon, okay? So on the one hand, around delta, t is much smaller than 1, right? Delta is much smaller than 1. On the other hand, epsilon, I will choose delta to be epsilon squared, right? So t is 1, but epsilon over, square root of t, but epsilon over delta is also going like square root of epsilon, so it's much smaller than 1, right? So for example, this is a good choice. But not necessarily. But okay, let's fix it on this choice. Okay? Now, I can take every power of epsilon that is smaller than 1. And it will work. Okay, now let's evaluate our integrals. What can we say about this integral? So, okay. This is the zeroth order is what? Is the integral from delta to infinity of e to the minus t, which is what?
Delta.
Which is e to the minus delta.
Yeah.
E to the minus delta. Right? And because delta is small, I can write it as 1 minus delta if you like, but okay. Now, minus epsilon times what we have now?
Gamma minus 2x.
Gamma
Or minus 1
of
x.
0 and delta.
Yeah.
Plus epsilon squared times gamma of
1 delta.
I guess that I have 1/2.
Yes.
Yes.
1/2 times gamma of 1 minus 1. Minus 1 and delta. Okay? Now, what about this integral? Now I want to make a change of variables. So I would like to define q as epsilon over t. And therefore dq, d or epsilon, epsilon is q, epsilon is q times t. Yes. And t is epsilon over q, and dt is minus epsilon over q squared dq. So I can write this integral as the integral from 0. Okay, first of all, I have e to the minus q times 1 minus epsilon over q plus epsilon squared over q squared 2q squared. You see it's the same structure as before. However, I have, what about the dt? Here I had the dt, of course, and now we have, epsilon here, and I will have dt here over q squared. Okay? And what else? What about the limits? So the 0 is now infinity,
Yes.
and I have a minus, this minus. So I will take off this minus and exchange limits. So here I have infinity, and here I have, if t is delta, then q is, if t is delta, then q is epsilon over delta. So what I have obtained here is what? I have epsilon times, what is the first term? The first term is incomplete gamma of minus 1 epsilon over delta.
Yes.
Okay? Now, I assume that, I erased it just now. I can't believe it. We assume that delta is going like something like square root of epsilon. So, epsilon over delta is like square root of epsilon, something like that. Right? So, it's still a small parameter. That's the important thing. What?
And they have the same order.
They have?
The same order.
Yes. Okay. Something like that. Good. Okay. Now I have to start collecting terms. So let's start from here. And again, both delta and epsilon are small. Okay? So I have 1 minus delta. This is from here. Okay? Minus epsilon times gamma of 0 and delta. Now this is, so I have minus gamma Euler, right? Minus ln delta plus delta. Okay, this I will neglect because delta is epsilon delta is smaller than epsilon. Epsilon delta is smaller than epsilon. And now I have plus 1/2 epsilon squared. I don't want epsilon squared. Okay, so this is what I got from here. Now, what I will get from here, I have now plus epsilon times this thing. So I have gamma Euler minus 1 plus ln of epsilon minus ln delta. You see, this is ln epsilon over delta. Minus 1 over x. X is epsilon over delta, so I have delta over epsilon. And the next term will be negligible.
Wow. It's multiplying by epsilon.
Because the next term is ordered epsilon over delta, so it will be epsilon squared over delta.
Yeah.
And epsilon squared over delta is epsilon to the power of 1.5 or something.
So the delta.
Okay. So now here is okay. So now the point is the important thing is that this delta, you have epsilon times delta over epsilon, so it's minus delta. What? No, not good. Not good. Did I? Okay, let's. There is a minus sign missing here. I think there is overall minus here. Why is that? Okay, I think, okay, let's first of all put this minus and then we think where it comes from. So we have 1. Now this delta will cancel by this delta. And here we have plus epsilon ln delta. Here we have,
Minus.
no, Oh, no. So, wait.
I guess I found a mistake.
What?
I guess I found a
Okay.
mistake. Then we change variables in the integral. We forgot minus. You see, t is minus
But
epsilon
change it
over.
Yes, but I
Yes.
exchanged the
Change
limits.
the limits.
Ah, well, okay.
So it's not.
See? Okay. What? So the only difference between what I have here and here is that I have a plus here. Meaning that we have a plus here.
Might have been.
Again, this is 1, right? This is n equals 0 of the 1. So we have minus 1 to the power of 0. And we have 1.
Oh,
And this is
side
minus. This is
yeah.
minus. This is sorry. This is plus. And this is plus. Right.
Now we have 5.
Now, we have this minus delta cancels with this delta, with this
Yes.
plus delta,
The line.
and what else? And we have here plus epsilon ln delta, and here we have minus epsilon ln delta. So this goes away with that. And what we obtained is
1 plus 2.
what we obtained is 1
Plus epsilon.
plus epsilons times 2 gamma Euler minus 1
Plus epsilon ln epsilon.
Plus epsilon ln epsilon. Okay? So, so first of all, when epsilon goes to 0, it goes to 0. It's a regular perturbation theory. Yes? But, I mean, I find this matching very nice. And we have integrated over 2 methods here. One of them is the expansion of the integral, and then the matching. Okay, fine. So having said that, and it's very, very important to be familiar with the integration with the gamma functions, because they appear everywhere. I mean, for me, I mean, in my research, they appear in many cases, and so there was once in Russia, there was very like 120 years ago, so on the end of the 19th century, many Jews converted to Christianity because this allows them to become citizens and to get all the rights. So there was one very famous guy that converted to Christianity named Hovelson, and he got his fame because he did not become an anti-Semite as you may expect, but still helped Jews. I mean, there was all kind of blood libels, and he used his status. He became a professor of Semitic something in the Empire University in Petersburg. And his son is the first guy who wrote the tables for. He was a mathematician, and the first guy that wrote the tables for the exponential integrals. But fine, so that's a Jewish connection.
May I ask you a question?
Yes.
What is your field of research in physics?
I'm doing complex system physics. A lot of actually, it's a combination of, technically speaking, it's stochastic processes and nonlinear dynamics. So, if you want statistical physics and nonlinear dynamics, the combination of both. And practically I'm working on many problems that have to do with birth-death processes, with applications to all kinds of things, from ecology to avalanches and collapses of systems and so on and so forth. That's at least during the last 10 years. This is what I'm doing.
It's more math, right?
I'm a theoretical physicist.
Yeah.
If I was an experimentalist, then it's another thing. But I'm a theoretical physicist.
You do math and hope that it will.
What?
You do math and hope it will be something meaningful in the real life.
Yeah. I mean, complex system physics. I feel that it gave me a perspective that many people do not have, and unfortunately no one will agree with me. But most of the complex system physicists are pretending, or most of the complex people who are doing complex science of complexity, right? Science of complex systems, believe in their ability to predict and to engineer complex systems. So the idea is, if you are looking at complex interactions, like, I don't know, between trees in the tropical forest, or between people, right? You said, I mean, this one is doing that, and it causes other one to do something else, or the spread of a disease, or things like that. If you are doing complex, the analysis of complex systems, then this will allow you to predict the future, the same way, that you can predict the projectile of a cannon, I mean, the trajectory of a projectile, and it will also allow you to engineer things. If you want to avoid, I don't know, extinction of a species or the spread of an idea or whatever, then it will allow you to, to engineer the system in order to avoid that. And I mean, my experience with complex systems is the other way around. So I think that complex systems are complex, and usually you can't do that. The interesting thing in complex systems, that's my perspective, is not to get handle on the system such that you can engineer it completely. But it's the other way, it's to understand what is possible and what is impossible. Because still, I mean, given initial conditions and given the laws of complex systems, there are many things that are possible, but many other things that are impossible. And there are many systems that apparently violate constraints on possibility of things. And this is true also, I mean, because, you know, condensed matter physics, don't tell anybody around out here that I told you that, but condensed matter physics is a science of complex systems. Condensed, I mean, a piece of copper is complex thing, right? And accordingly, the problem is that the way we are teaching physics, we jump over gaps. Because nobody wants to say to the students, well, we don't understand anything, right? So you have one course that is started by, you know, assuming something and developing on that, and you have another course that is starting in assuming something else and developing on that, and the intermediate range is not described usually to the student. Maybe we should have a course about, you know, the things that we do not understand. For example, why the only magnetic materials are, the only magnetic elements, right, are nickel, cobalt, and iron. Nobody knows, right? So essentially, you want to believe that since everything is understood, you know what an atom is. You have a nucleus, and you have electrons, and you know what you know the Schrödinger equation, and you can calculate essentially everything, right? That you will be able to predict which element is going to be magnetic and which element is going to be non-magnetic, right? Nobody knows. So what we are doing, I mean, as teachers of physics, we are showing Schrödinger equation, blah blah blah, in a quantum mechanics course, and then in the what's it called? In the condensed matter course or course about magnetism, we are saying, okay, let's write. We have Ising model, right? Every spin, yes. But why J is large and negative? Nobody knows, right? And it's a very peculiar property of only 3 elements, right? Now, of course, for these 3 elements, because people are working on this problem 70 years, 60 years now, right? Work very hard on this problem. Then, of course, there are excuses. There are all kinds of calculations, blah, 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 ab initio, blah, blah, that show that iron is ought to be magnetic. However, nobody can use this theoretical framework, which apparently explains things, in order to predict what will be the magnetic properties of an alloy, right? So now I have an alloy of 20% iron and 80% magnesium. Is that going to be magnetic or not? You have to check. I mean, the only way. I mean, nobody can use the so-called understanding of exchange energy and all kinds of buzzwords that people are mumbling when they are asked about that, in order to predict or to plan, right, to engineer new materials. What people are actually doing, they are just playing with materials, just cooking many compositions and are trying to find something. And of course, they have some insight that gives them some rules that you know, if you have too much of that, then it's not good, and something like that. But nothing than that. Same thing about superconductivity. You are cooling a material. Is that material is going to be superconductor or not? Nobody knows how to predict it. Despite everybody know how to speak about, you know, Cooper pairs and pairing mechanism and blah, 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 blah. Nobody knows how to predict for a priori for a given material if this material will be a superconductor and in what temperature it will cross over to superconductivity. Right? It's so complexity is complex. So I mean, the weird thing is that we understand something. I mean that the trajectory of Mars or Venus or the hydrogen atom is a simple system. That's this by itself is I mean very nice, but there are many. In many cases, we are sort of jumping over the them things that nobody knows to explain, and are saying, okay, let's write an effective Hamiltonian. And now we are writing what we call London equations, and everybody are happy. But these are phenomenological equations, not
all the standard model.
What?
All the standard model is just phenomenon.
No, the standard. Okay, you can say that everything is phenomenology. No, the standard model is supposed to describe. It may be the elementary physics.
Yes, but how you derive it? You just take the Lagrangian.
Yeah, okay,
and
fine.
add all the terms that you know.
Okay, but maybe this is a fundamental physics. I mean, except that it cannot explain neutron oscillations.
Yeah,
and,
it's more of guessing than just.
What?
It's more of guessing.
No, it's not guessing.
No, the Lagrangian is guessing.
They guess. No, but okay, fine. You can say that every theory is a guessing. For Newton, saying that GM1 M2 divided by R squared is also a guessing. It's a guesswork. But
it's a good guessing.
Yeah. So
It's a good guess.
for Newton, it was a guesswork. I mean, not for us.
But we can write an equation that describes complex system also in the microscopic level, not only in the
Right, but nobody knows. You can write. This is exactly the point. You can write, unlike I don't know, models for spread of a disease. These models have no, nobody derives them from fundamental equation, right? It's just an assumption that, people are meeting every now and then, and there is a finite chance of an infected one to infect a susceptible one, and then so let's write some equation of that, I mean, exponential growth, and then there is a saturation, and so on and so forth. This is something that, but in condensed matter, you have the Schrödinger equation. So you can, in principle, you can write the correct equation to all the electrons of an iron atom. And then you can add another iron atom and another iron atom, and you will, it's supposed to support ferromagnetism, despite being completely unintuitive, because the fact that they want to be in the same state of the same spin state implies that they cannot exchange, right? So it's supposed to increase the temperature, not decrease the temperature. So you have a phenomenon and you want to have it with the inverse sign, and people are working it for, I guess, since 1950 at least, for 70 years. No, I mean, I'm sure I'm not tracking it. So maybe, I'm sure they have all kind of very complex simulations or theories with 25 types of diagrams that explain why iron is magnetic. But you cannot use it to, as I told you, cannot use it to engineer, to predict the Curie temperature. It's nice, but it's not useful.
But it's, well, I don't know, but it's at least the impression I got from the bunch of studies that always the experiment come before the theory. Maybe in some very
not
special
necessarily.
cases.
Yeah, people in many occasions.
Usually there is an experiment.
Theoreticians have suggested a phenomenon, and then the experimentalists
But
came
usually there is an experiment, and then we try to
discover
explain
it.
it. There is an experiment, we don't know how to explain it, and then we think how to explain it. And if we are able to explain it, everybody
In many cases this is right, and in many cases it's the other way around. I guess that in most cases you are correct, yes. But as it was once upon a time was there was a note on the door of the lab of Aviad. It said that a theoretical result is a result that nobody believes except of the one who derived it, whereas an experimental result is a result that everybody believes except the one who did the experiment, right? Because he or she knows all the dirty things. Okay, next. So now let's speak about the second method, which is the integration by parts. So what is my example? Yes. So my example is, I want to calculate the integral from what? From x to infinity. So from 0 to x of e to the minus, what's going on here? Yes, e to the minus t divided by the square root of t dt. That's it. Right? And I want to expand it as x goes to infinity. Now actually we know what it is going to be, because, okay, we can do that with the gamma functions, because this is simply gamma of 1/2. That's no, I have to change the variables. So, but essentially it's the structure, but I want to do that when as x goes to infinity. Okay, when x is infinity, then it should be gamma of. Okay, so but I want to do that using integration by parts, and I have a problem because I'm going to write this as the integral from 0 to x of 1 over the square root of t times d dt of e to the minus t minus dt. Right? That's correct. However, now when I will try to, so I have minus 0 to x of e to the minus t over square root of t plus an integral from 0 to x of, so I want to derive t to the minus 1/2. So I have one minus here, I have another minus, and I have 1 over 2 times t to the 3/2 times e to the minus t dt. And what is the problem? The problem is that this diverges. When I'm plugging the lower bound, the lower value, it diverges. Okay, that's not good. So instead of that, we can write this integral as the integral from 0 to infinity of t to the minus 1/2 e to the minus t dt minus the integral from x to infinity of t to the minus 1/2 e to the minus t dt. See? And because this is, as we say, this is a gamma of what? Of 1/2, which is pi over 2 or something like that. What is gamma of 1/2? Square root of pi, sorry, yes. Yes, so this is gamma of 1/2, whatever it is, minus, and now I will write it as the integral from x to infinity of t to the minus 1/2 d dt plus of e to the minus t dt, which is gamma of 1/2, and now I have plus x infinity of e to the minus t over square root of t. So it will be gamma of 1/2 plus minus of course, e to the minus x over square root of x. That's the first term, and by integrating by parts, we can calculate the whole series. That's the leading correction in X. Okay? Yeah. Fine. And we can make a progress by using this integration by parts method, even in cases that appear to be very bad. So for the moment, let's try to find I is the integral from 0 to x of e to the t squared dt when x goes to infinity. Yes, at large x. The large x is function of this integral. Now, if I want to use the integration by parts method, I will write that as an integral from 0 to x of d dt of e to the t squared dt, and this will give me 2t, so I have to divide by 2. Right? So the leading term will be 0x of e to the 2 squared over 2t, and this is infinite.
Should be minus exponent or
No, it's plus. That's a
di-
problem.
divergent.
That's a problem. Yes, but I want to know how. Does it diverge like e to the x squared, or like x to the x squared, or like e to the x cubed? How it diverges?
Okay.
Right? I want to know how it diverges. What leading term as x goes to infinity. Okay? And this is a lost cause. Now, you may think maybe I can use the method I used here.
Yeah.
But this also is not going to work because you want me to calculate 0 to infinity of e to the t squared dt minus integral from x to infinity. Now I can calculate this integral, but not this one. This one diverges as well. Okay. So what can I do? Okay. So in order to solve this integral, I note that this divergence at 0 is not, it's not, it's just an idiotic thing that is not important, because the real divergence is coming from the upper limit, not from the lower limit. So in order to do that, to analyze that, what I will do is to write this as the integral from 0 to a of e to the t squared dt plus an integral from a to infinity to x of e to the t squared dt. Okay, now what this integral will give me, this integral may be written as the integral from a to x. Again, now I can write it as 1 over 2t e to the d dt of e to the t squared, which give me in the first a and x, it gives me 1 over 2t e to the t squared. So this gives me e to the x squared over 2x minus e to the a squared over 2a. This is this integral. What about this integral? In this integral, I can simply expand t because a is small. So I can write it as sum from n equals 0 to infinity of t to the 2n divided by n factorial. And I am integrating from 0 to a. dt, right? So this is a sum from n equals 0 to infinity. This will be t to the 2n plus 1 divided by 2n plus 1, so it will be 8 to the 2n plus 1 divided by 2n plus 1 times n factorial. This is this integral, and this is that integral. Now, you see that when x goes to infinity, all this is garbage, and all this and this one is, I mean, all these are not interesting in the limit when x goes to infinity. So the only contribution is e to the x over 2x. X squared. Yes. E to the x squared over 2x. This is a leading contribution, and now you can do the same, and of course you always get the contributions from the upper limit and not from the lower limit. So all the lower limit contributions will be subdominant.
It's some sort of asymptotic matching, but without matching.
No, okay, yes. I mean, okay. We did the
split,
same. Yes,
yeah.
we split it, but
Yeah.
what we obtained is that the only asymptotic, the only
Leading on.
leading order in the asymptotic limit is coming from this term. All the other terms are subdominant, and they will still be subdominant to any order in perturbation theory. Okay, now let's discuss one case in which one important case to show in this context of integration by parts method So I see that I will not have time today to actually give you an exercise about the Laplace integration, so this will be next week. And I will speak further on the Laplace integration method, so we will be able to solve more complex problems. Okay? So another problem to solve with the, okay, so let's try to solve the integral from 0 to infinity of e to the minus ax squared dx, or at squared. Wait, xt squared, yeah. Right, in the limit of large x. So of course this is it's not, we know what the answer is, right? But what, because this is half of the Gaussian integral. So the answer, just to remind ourselves, the answer will be square root of pi over x divided by 2. That's the answer, right? And the answer for any x. But we want to examine this as x goes to infinity. This is an analytic answer. Forget about it for the moment. Suppose we don't know it. And we are trying our luck with the integration by parts method. So we can write this as the integral from 0 to infinity of d dt of e to the minus xt squared dt, right? And this d dt will give us, and we have here 1 over 2x t with a minus. Right? So what we are going to get is a minus from 0 to infinity. The first contribution will be e to the minus xt squared divided by 2xt, and clearly this diverges. Okay. Yes. Okay. Yes, this diverges from the lower limit. Okay, and you can try, the cures with it. If we, okay, so you are saying maybe we can divide it into the integral from 0 to a, and the integral from a to infinity, and you will find out that this also diverges. because now the main part of the integral is coming from the vicinity of 0. Moreover, there is a deep reason because you see that the integration by parts method, what it gives you is something that goes like e to the, I don't know, e to the x, I mean, something like that goes like 1 over x, 1 over x squared, 1 over x cubed. Not necessarily these powers, because we can have 1 over x to the 4, 1 over x to the 7, and so on. But it's always integer powers of x. And we know that the answer is going like 1 over square root of x. So for that reason, the integration by parts method, I mean, this is not a reason. This is an indication that the integration by parts method is not going to work. Okay, now, okay, so just because I have still have 7 minutes, so in these 7 minutes we can do something about Laplace method. So suppose somebody is asking you, what is the integral from 0 to 1 of sine t, sinh t, sorry, times e to the minus x sinh to the 4th power of t dt at x goes to infinity.
So we will not evaluate the previous integral.
What?
We will not evaluate.
You know the answer, right? But you can evaluate it with Laplace integral. It's a trivial example of a Laplace integral, but not by using integration by parts.
Ah, okay.
You cannot find the asymptotic of this integral using integration by parts. Okay? So I want to solve this problem using Laplace method. So first of all, I'm asking what is phi of t? Sinh to the 4 of t, right? And what? And we are interested in the region between 0 and 1. From where I will get the biggest contribution? What?
1.
1. You see?
Yeah.
I must get the biggest contribution. No. Why are you saying that? It's e to the minus. When x sinh is 0. Sinh of 0 is 0.
Ah, okay. So we will get.
No. We get the biggest contribution will come as x goes to infinity from t equals 0. Right? But, okay, so how, so I can, okay, it's not exactly, okay.
So phi is minus.
Yes, phi is minus.
So what?
Phi is
Minus.
minus.
Phi is minus.
Okay.
Now,
Okay? And what will be phi prime of 0?
Minus 4.
So phi prime is minus 4 sinh cubed times cos. And it's 0. Right? What will be the first power? I mean, what about phi double prime?
Also
It's also 0 because now okay.
Still
So
have
what will be the first power that will not
4.
4? So if I am taking fourth derivative, then and I'm taking only from the sinh, right? Because if I'm taking the cosh, it will be a sinh again. So if I'm taking fourth derivative, I will get 4 factorial, which is 24, right? Times what? That's it. times cos to the 4.
So you have a minus.
Minus
Okay.
also.
With a minus. Yes. So at the vicinity of 0, I can write this as integral from 0 to say epsilon, doesn't matter, right? Of, but since t, when t is very small, what I'm going to get simply t, right? Note that this is not a classical. What I'm doing is Laplace approximation, but with many tricks. Because in the Laplace, I told you take this function at the value of c, but c is 0. Or I mean, at the value of at the maximum, but the maximum here is at 0. And this function, which is the f of t in the Laplace method, is 0 at 0. So I'm just I'm doing it step by step, right? So what I will get is t times e to the minus 24x times times t to the 4.
Yes.
Yes.
The upper limit of the integral is 1.
What?
The upper limit.
And of course, after writing it that way, I will extend it to infinity, the same way I did in Laplace. So what's the answer? So we have to define Q to be 24 times x times t to the 4th power. And then t is q over 24x to the power of 1/4. So dq is q to the 1/4 minus 1 divided by 24x to the 1/4. Okay? And what I will get an integral from 0 to infinity, yes, because it doesn't matter. Now t is q to the 1/4 over 1 over 24x to the 1/4. Sorry. Times, this is t. And now I have q to the 1/4 minus 1. So it will be q to the 1/2 minus 1 e to the minus q dq, which is gamma of 1/2. So what I have obtained is gamma of 1/2 divided by 24x to the power of 1/4. So this is not actually, it's not a canonical example of Laplace method, but I used the idea.
Don't
Yes.
you need to count 24x twice? Once on the t and once on the dt?
Ah,
I mean, you wrote dq, but you meant
yes,
dt,
yes, yes,
right?
yes, yes. You're right. You're right. I have.
It's the square root.
Sorry,
of
I need dt. So this is dt, and okay. Sorry, and I have the t. The t dt, so I have it to the 1/2. Yes?
Yes.
So it will be 1/2 here, and this is, gamma of 1/2 times, so this is 6 square root of 6 times 2 times square root of x. Right? And this is square root of pi, right? So I will have square root of pi over 24x. Okay, which again, you see that it will not work for you if you try integration by parts, because you get fractional powers of x. Okay, So this was the exercise for today, and I still owe you homeworks. And next week we are going to continue with the Laplace method. And then I still hope to sneak the two-time perturbation because it's important in many situations. And yeah. Okay.
Thank you very much. כן, תשמע, השעות האלה קשות, מה זה קשות, אחי?
אני אחזור, אני יכול, ואם יהיה לי כוח אולי אני אמשיך קצת קוונטים, אבל לא נראה לי זה כבר יקרה.
אין סיכוי.
הבא שמחר אני באמת מה לעשות קוונטים. לא יודע צרות למחר. תחשוב גם מחר אותם שעות.